Welcome to the Equatorial Coordinate System module. In this module, you'll become familiar with the equatorial coordinate system and be introduced to more complex aspects of the time evolution of the celestial sphere. To prepare for this module, you should already have viewed the celestial sphere module, the introduction to stellarium module, and the horizon coordinate system module. Let's begin. We begin with a display similar to the past two modules. We're currently located in Toronto, Canada, on July 1st, 2022 at about 8 a.m. Our field of view is about 90 degrees, and we begin with a flat, solid horizon, so we're using the perspective projection, as you well know. Now, before we change any parameters, I'd like to show you why I didn't use the perspective projection for these modules, even though you might think a flat horizon would be more appropriate or at least more intuitive. So to do this, I'd like to select the azimuthal grid or the azimuth altitude coordinate grid that we learned about in the horizon coordinate module. Now look at the distortions in this grid. Each of the different cells are different from one another, or the adjacent cells. This cell is radically different, to our eyes at least, than this cell, for example. So this would introduce challenges to some of our visualizations in this and the last module. I will now change some of the parameters, but first let's turn off the azimuthal grid. First, we'll change the projection. So sky and viewing options window from the left-hand menu. Click on it. Sky option. We'll use the hammer ATOF, my favorite, as you're well aware. With markings, we're going to turn on the celestial poles. I will not turn on zenith and nadir for the moment. That will come later. And the landscape, well, I'm quite happy with zero horizon for this visualization. So I'll click on that and we see that in fact for Toronto and the characteristic, to the eye at least, curved horizon. Now I'm going to show you how to add a custom location for the observer's position. So we click on the location window, the top icon in the leftmost menu. And what I'd like to do is to add a fictitious place that's not far from Bismarck, North Dakota, or Winnipeg, Manitoba, that is right on the Canada-US border, latitude of plus 49 degrees and longitude of minus 100 degrees or 100 degrees west. I'm going to call this location Can-Am. So let's first type in Can-Am to see whether there is a place like that. It would be surprising for me. And in fact, there isn't in the database. So we're going to have to enter it manually. The first thing to do in the lower half of the window is to give it a name, this location, Can-Am. Then change the latitude to 49, and I'll make it exactly. So 0 arc minutes and 0 arc seconds. And the longitude will be 100 west, 0 minutes, and 0 arc seconds. The elevation is fine for our purposes. So we click on this and we add it to the list. And in fact, it's now in the Stellarium database, as we can see from the bottom menu. So we exit and now turn on the cardinal points. Recall north, south, east, and west, and the intermediate points. We're going to face south. Capital S ensures we're facing due south. We're going to turn on the meridian. Recall semicolon. And the celestial equator. Recall period. Now let's turn on the stars and the names of the stars. Lowercase s turns on the stars, and Alt S turns the labels for the stars on. Now let's turn on the azimuthal grid once again. Now recall the azimuthal grid, which measures azimuth along the horizon. In fact, I can turn the compass marks on, and the altitude, the angle above the horizon at a constant azimuth. And this particular grid is fixed to the observer's location, and objects move underneath as the celestial sphere rotates about the observer. To illustrate that, I'm going to, in fact, move time forward. Recall that motions, temporal motions, are governed by these four icons here. This is move in the past, move towards the future, pause and play, and we'll ignore this particular option which sets to clock time of the device, or something that you've already pre-programmed into Stellarium. Avoid clicking this. This actually quits the program. So let's click this maybe 3 times just so you can detect motions of the stars. So you see here that Sirius has just risen over the east or southeast horizon, Rigel, Aldebaran, for example, and some of the other stars. And what's happening here is that the stars are increasing in azimuth and altitude on the eastern half of the sky, which is of course to the left of the observer's meridian. I'm talking now not about the circumpolar stars and not about never-rise stars. And so I'll pose the question, like I did in another module, what is the maximum altitude a star will achieve on the celestial sphere? And that maximum altitude we answered in a previous module, but when it achieves that is important in this context. And I'll speed the motion up slightly so we get some stars. We see that it occurs when the star transits. Recall, transit is when it intersects the observer's upper meridian for our purposes. So when it is past transit, it's in the western half of the sky. The azimuth continues to increase, but the altitude decreases until eventually it sets, and the horizon, of course, has an altitude of 0 degrees sometime later. So we're going to pause for a moment. We see that azimuth and altitude change continuously with time and with location, because my zenith, which helps to define my meridian, is different from your zenith. So we concluded in our last module that a more universal coordinate system, a system using Earth's symmetries, would be very useful. And that system is the equatorial coordinate system, the system we're going to learn about in this module. It's a celestial analog to the longitude and latitude system on Earth. Now imagine lines of longitude and latitude on Earth's surface instantaneously projected onto the celestial sphere. How would that look? Well, let's turn off the azimuthal grid and turn on the equatorial grid. So this is what you might see. The analog to longitude, which these are lines, is called right ascension, or RA for short. Well, the analog to latitude is called declination, or DEC for short. Now, unlike in the horizon coordinate system, celestial objects maintain a unique and fixed RA and DEC with time. So I'm just going to turn on the celestial sphere in the forward direction, and you'll see, I hope, that the grid and the stars follow together. It's as if the stars are painted on the grid, but the grid itself is rotating or revolving about Earth once per day. Now, declination is an exact analog to latitude. celestial objects outside the solar system move along lines of constant declination. These are also called diurnal circles, daily circles. They're small circles on the celestial sphere, except for the celestial equator, of course, which is a great circle. The celestial equator is the 0 point of declination. And we see here, if your device has sufficient resolution, this is plus 10 degrees dec, plus 20, plus 30, minus 10, minus 20, etc. Now the north celestial pole should have a declination of plus 90 degrees and the south celestial pole minus 90 degrees. So let's face north and see whether this is so. And in fact, the NCP designation is eclipsed by the Polaris designation here, but this is 90 dec, 80, 70, 60 declination, 50, 40, etc. So capital S to return facing south. Now right ascension is analogous to longitude, except as you've seen that the entire grid moves or revolves about Earth daily. Like longitude, lines of RA are great circles on the sky. And lines of RA are parallel to the observer's meridian, and again, lines of dec parallel to the celestial equator. While a celestial object has a fixed RA and dec, the challenge for the observer is, where do we look on the celestial sphere at this moment to find it? We know the object lies somewhere on its declination circle, but where? And that's going to be the subject of the next few minutes in this module. But first, RA can be measured in degrees, from 0 through 360, much like the azimuth. But it's more common and convenient to measure angles in right ascension using units of time, that is, hours, minutes, and seconds. We're going to illustrate this now by moving to the star Fomalhaut in the southern sky. It's still visible from Can-Am. Now I happen to know that if we move the sky backwards, we'll be able to locate Fomalhaut most quickly. We could also go forwards, takes a little more time. So I'm going to click on reverse time and see and find and identify Fomalhaut right here. So we see the reason I'm using Fomalhaut is it's almost exactly at the intersection of this particular grid pattern. So it's very helpful for this illustration. So Fomalhaut is on a line of RA designated 23H, meaning 23 hours. And of course, we're going to try to understand where the 0 hour line of RA, the 0 point for RA, comes. So it's on 23 hours, and in fact, it's at minus 10, minus 20, minus 30, almost degrees declination. So what we're going to do is we're going to move Fomalhaut right on to the meridian. In other words, freeze it when it transits. Admittedly, it's going to be in backwards time direction here. And then once we have Fomalhaut on the meridian, we're going to check how long it takes this particular line of right ascension to then transit or become coincident with the observer's meridian. Hope that's clear. So let's go back a little bit till Fomalhaut actually transits. And that's pretty close. Okay, freeze it. Now I'd like you to see that it's 5:01 here in time, and now I'm going to move the celestial sphere forward until this particular line of RA intersects or is coincident with the observer's meridian. Okay, So now it's 6:02. So not too bad reflexes here, so exactly 1 hour of time, give or take. So indeed, the time it takes to move one main grid spacing in RA is 1 hour. And this is why RA is labeled in 23 hours, 22 hours, 21 hours. And it's not 24 hours, it's actually 0 hours, again, 1 hour, 2 hours, 3 hours, etc. So we've shown that each of the vertical grid lines is spaced 1 hour of time apart. What about in angle measure? So what does this angle subtend from our location? Well, we can calculate that very quickly. If Earth rotates once each day, or 24 hours, then in 1 hour it rotates through 360 degrees divided by 24 hours, or 15 degrees per hour. Now I'd like to impress upon you the fact that even though these lengths look different, they still represent the same underlying angle. And to illustrate that more effectively, let's face north. And again, this angle is 15 degrees, that angle is 15 degrees. They're all 15 degrees. Face south again, capital S. Now the 0 point of right ascension was arbitrarily established as one of the points of intersection of the ecliptic, or its orbital plane, with the celestial equator around the time of Hipparchus, let's say 300 BC or BCE. It was in the constellation of Aries, the Ram, and was called the first point in Aries. So what I'm going to do now is to turn on the ecliptic. Recall, comma. It's the orange line. And we see, not by coincidence, that the intersection point is right about here on the celestial sphere. This is the 0 point of right ascension, the first point in Aries. Now you're probably thinking to yourself, well, we have two great circles on the sky, neither coincident nor parallel, so they must intersect in 2 points. So why this particular point? Okay, so some explanation. So the sun, of course, moves along the ecliptic throughout the year. When it crosses the celestial equator moving north, this is called the vernal or spring equinox. An equinox meaning equal lengths of time, day and night, in principle. In practice, it's not the case, and you can discuss in your class why that's not the case. So this is the vernal equinox, and recall that the inclination between these two lines, of course, or planes, is 23.5 degrees. So now let's look throughout the year along the ecliptic to identify a few other major points. So I'll move time forward, but I want to impress upon you the fact that the sun at the vernal equinox, the 0 point of right ascension, is moving towards the north, that is, into the northern hemisphere, to positive declination, so moving in this direction. So let's start the celestial sphere in motion. So the sun is moving up here with time. We started out in July. We're not going to follow it throughout the entire year, just to say that the sun achieves a maximum declination at the summer solstice around June 21st, about 23.5 degrees north, or plus 23.5 degrees. Solstice means sun standing still, and that means, well, the sun is not going to get any higher in declination. It stops for a moment before heading south along this line. When the sun crosses the celestial equator, again, it's called the autumnal or fall equinox, and the sun then moves into negative declinations. And then finally, the sun achieves its minimum declination, minus 23.5 degrees, at the winter solstice, about December 21st. So let's go back to where we came from. To the first point in Aries, to the 0 of right ascension. The autumnal equinox is now in Virgo, but it used to be in Libra. In the same way, I'm going to illustrate by turning on the stick diagrams for the constellations and the names of the constellations, and show curious fact that in fact the 0 is not in Aries, but in fact in the constellation Pisces, the fish. Why is that? And you'll probably recall the phenomenon of precession, or precession of the equinoxes is to blame. You will learn a great deal more about this in your course. But one thing you can do with stellarium to show just a little bit of its power is to move the time back to Hipparchus's time. Let's say 300 BC or BCE, and let's see where the first point in Aries was then. So you click on this, and I'm going to show minus 300. You have to use minus to indicate BC or BCE. And we see now that the point of intersection is indeed in Aries the Ram, the constellation Aries. Very powerful. Stellarium can be used to visualize a great deal of contexts. Okay, let's set the time back to 2022. You see you can move forward in time as well. Though we know the right ascension of a celestial target from a catalog or some other resource, again, we return to the question, where do we look on the celestial sphere at any moment to find it? We know it's somewhere on its declination circle, but where? So I'm going to turn the constellation and their figures off for the moment. If we knew where the first point in Aries was on the sky right now, then it would be a simple matter to move along a line of constant declination either to the east or to the west. But that's not always practical, as you might imagine. What happens if the first point in Aries, the 0 of RA, is in the daytime sky, for example, if you're a nighttime observer, 12 hours away? Better is the following way. The right ascension of the celestial meridian, at least the upper celestial meridian, is called the sidereal time. Now, sidereal refers to star in Latin. So what exactly is star time? And why isn't it the same as solar or Sibyl time, the time we keep as society? So what I'm now going to do is to move back to a richer part of the celestial sphere near the constellation of Orion, where we began this module when we said on Can-Am. So let's move time forward. So we have a lot more stars as reference points. What I plan to do now is to advance the celestial sphere in time increments of exactly 1 solar day, 24 solar hours. Now, a solar day is defined as the time between successive transits of the mean sun. Now, there's a distinction we'll make shortly between the mean and apparent sun, but for the moment, let's just call this the successive transits of the mean sun. So I'm going to advance the sky in increments of exactly 1 solar day by typing the equal sign. And I want you to focus on one of these labeled stars. Okay, and notice the time here, July 1st, 11:02. So here I go clicking equal sign once. Now it's July 2nd, 11:02, twice, 3 times, 4 times. We're advancing 1 solar day each click of the equal sign. Now notice that the stars are moving gradually westward from day to day to day at the same solar time. By how much? By about an extra 4 minutes per solar day. And we can see that by, in fact, putting this line of right ascension onto the observer's meridian again, and then watching how long it takes that meridian to slide over 1 grid spacing. So let's move that RA onto, not bad. Now I'm going to calculate or measure how long it takes that line of right ascension to slide over to here. So keep your eye on it. 1 equal sign. Now the 6th of July, 7th of July, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So approximately 15 days, the celestial sphere at the same solar time slides over by 1 hour in right ascension. A sidereal day, by the way, is defined as the time between successive transits of a star, any star. A sidereal hour is 1/24th of a sidereal day, a sidereal minute is 1/60th of a sidereal hour, and a sidereal second is 1/60th of a sidereal minute. So the sidereal day is about 23 hours, 56 minutes, and just over 4 seconds of solar time. So it's shorter than a solar day, as you can see. This is why stars move slightly to the west from day to day to day. The entire celestial sphere gradually slides westward throughout the year, which is why we see different constellations at different times of the year. Now, why is the sidereal day shorter than the solar day? You'll no doubt discuss this in class, but it's the result of Earth not only rotating on its axis, but revolving in the same counterclockwise direction about the sun. So let's move the celestial sphere in increments of 1 sidereal day. So let's put the cursor right under Aldebaran, and I'm going to move in increments of 1 sidereal day, Alt equal sign. So take a note, it's July 20th. Here I go, Alt equal sign. It's July 21st, as you can see. Again, again, again. The stars don't move. They're frozen onto the celestial sphere, as it were. But now very closely note the time of the day here. Does that reproduce exactly? So let's look. It's 10:29:29. Alt equal sign. 1 day advance, but now it's 10:25, 4 minutes shorter. Again, 4 minutes shorter. So this is solar time down here, but the sky is moving only in sidereal time. That is 1 sidereal day. So the stars appear to freeze on the sky, but only advancing 23 hours, 56 minutes, and 4+ seconds at a time. Now, if we know the sidereal time, that is the right ascension of the observer's meridian, then we can move directly to where the object is on the celestial sphere. If the RA of the object is greater than the sidereal time, the object is east of the meridian. If the RA is less than the sidereal time, then the object is west of the meridian. Now, what about the sun? Does the sun freeze on the celestial sphere when we move in increments of exactly 1 solar day? Well, if you think about it, clearly not, because from the summer solstice to the winter solstice, the sun moves from +23.5 degrees deck to -23.5 degrees deck. So you might think at first that the sun just slides at noon up and down the observer's meridian from plus 23.5 dec to minus 23.5 dec and then back again in 1 year. So let's look at this. So what I'm going to do is to turn off the ecliptic, comma, star labels, Alt S, the stars S, and I'm going to turn on the planets, lowercase p, and the labels, Alt P. And we see here the sun, in fact. And now we're going to move the sun closer to the observer's meridian just for purposes of illustration. So let's move the clock or time celestial sphere forward in time until the sun is roughly near the observer's meridian, near our meridian. Okay, so we've paused. I'm also going to maybe get rid of the equatorial grid just for the moment. Now what I'm going to do, and I should remove the azimuthal grid since it's not helpful at the moment. What I'm going to do is advance this view of the sun, which you must focus on. I can't get the sun in isolation. The planets and the moon come with it. So it'll be a bit busy and could be a bit chaotic, but if you just focus on the sun, this will be clearly illustrated. So if I hit, now it's July 26th, 2022. If I hit equal sign, notice it's July 27th, the same local time. So I'm going to keep the equal sign down, and you'll see from day to day to day to day as time advances. Let's see whether in fact the sun engages in this up and down motion from plus 23.5 to minus 23.5 back up to plus 23.5. Okay, here we go. Equal sign, and I'm holding it down. Notice that the sun is in the western part of the sky, now in the eastern part of the sky, now in the western part of the sky, back to near the meridian. Somewhere near where we've began, but 1 year later. So the sun appears to trace out a figure 8 on the sky called an analemma. This is the apparent or actual sun. It does not transit exactly 24 hours later, day to day to day, but it can be slightly shorter or slightly longer. And over the year, it traces out this figure 8 pattern again, which is called an analemma. Now, stellarium is very powerful for a number of reasons, but it's powerful also because I can illustrate this effect even more clearly using a type of video or movie that it has produced, or a script. So if I click on configuration window and click on scripts, you'll see that the first is an illustration of an analemma. So what I'm going to do is click on this and you will see this actual shape. I think the time increments are not 1 solar day, but maybe a few solar days, just because it would be too busy on the sky showing day to day to day, but it's a constant increment in solar time. It's going to end rather abruptly, and I will have to change some of the parameters back to our parameter set. That's just life. So there may be a little bit of discontinuity between the analemma script and our return to our module. Okay, so I'm going to click on the analemma. Here we go. We see the sun. We see the Hammer-Ehthoff projection, the azimuth coordinate grid, and we see the sun beginning at winter solstice, moving to northern declinations, but there's your summer solstice tracing out this figure 8, this analemma. So again, this is the actual sun. So now I must reset the parameters. Now, what causes this analemma? This is because of two factors. Earth's equatorial plane is tilted by about 23.5 degrees from its ecliptic plane. This is called the obliquity of the ecliptic. But also because Earth's orbit is slightly egg-shaped or elliptical in shape. It deviates by less than 2% from a perfect circle, but nonetheless, this has a significant effect. You'll learn more about this in your astronomy course. Now, the apparent sun, as I've indicated, is the actual sun, while the mean sun is a fictitious point on the celestial sphere that moves with a constant angular rate throughout the year. Civil time is based on mean solar time, and the mean sun transits at noon local time, at least without time zones. By the way, the quantity equation of time is defined as the difference in the transit times of the apparent sun and the mean sun. And of course, you need the equation of time to convert between sundial time and civil time. And the equation of time could go from about minus 15 minutes to about plus 15 minutes, give or take a minute or so. Now let's reorient our view towards the star Fomalhaut, meaning, by the way, eye of the whale in Arabic. I'll turn on the equatorial grid and move backwards in time to reach Fomalhaut. Okay, so here's Fomalhaut again, and it's about 25 light years away and among the 20 apparently brightest stars in the sky. So recall, if you click on Fomalhaut, hover the cursor over it, left click, you'll see its name indeed, and a series of appellations from different catalogs, cultures, and a wealth of information here. Now, we've looked before rise, transit at set times, and azimuth altitude. But now you understand a few more records here. The right ascension declination, about 22 hours and 57 minutes, nearly 23 hours, and that's exactly what we see here. And the declination of minus 29 degrees and 37 minutes, almost minus 30 degrees. Now, there are two records here at different epochs. And because of precession, you have to be careful of when you specify the location of an object on the celestial sphere. So these two differ only by virtue of their epoch. This is current, that was the year 2000. Again, you're familiar with the azimuth altitude, rise, transit, and set times. The mean sidereal time is something new to you. This is again the right ascension of an object identically on the observer's meridian, 23 hours, 28 minutes. And of course, it's larger than Fomalhaut's right ascension, so it is to the east of Fomalhaut. I'd like to draw your attention, however, to this particular line or record, HA and dec. Well, dec you know, declination, but what's HA? Well, it's the last parameter about which we'll speak in this module, a very important parameter for identifying objects on the celestial sphere, and it's short for hour angle. The hour angle is the difference between the sidereal time, that is the RA of the meridian, and the right ascension of the celestial object of interest. Hour angle is measured in units of time, just like RA, hours, minutes, and seconds. Notice the hour angle for Fomalhaut. It's about half an hour, 29 minutes. So 0 hours, 29 minutes. And we see that it's right in between the 24-hour or 0-hour line of right ascension and 23 hours right ascension, which is the right ascension of Fomalhaut. So somewhere right in the middle, and indeed the hour angle is about 30 minutes. Now the hour angle is positive to the west, meaning that Fomalhaut transited about 29 or 30 minutes ago. If the hour angle were to the east, it would be negative If Fomalhaut were over here, it'll be negative 30 minutes, meaning it will transit in 30 minutes. Now, Fomalhaut will transit again in 23.5 hours, but it has to go all the way around the celestial sphere again. We prefer to use smaller numbers, either negative or positive, for our angle. Now, the concept of hour angle makes it easier now for any observer to identify a particular location on the celestial sphere, whatever her location. To find an object, we move to its declination or diurnal circle, and then we calculate its hour angle based on its right ascension and the sidereal time, or the local sidereal time. And then we move, if it's negative, to the east, so many hours, minutes, seconds, or to the west if it's positive, so many hours, minutes, and seconds. So there we have it, how to identify a location on the celestial sphere given right ascension and declination and the local sidereal time or sidereal time. It's understood it's local sidereal time. Now the planets and moon have different periods because they also have their own orbital motions. Recall they periodically engage in retrograde motion, as we learned from the History of Astronomy module. Finally, what is the declination of the observer's zenith? So recall, the zenith is the point directly above an observer's head. That, of course, is the intersection of a line from Earth's center through the observer and intersecting the celestial sphere. Pause this module and try to figure it out. From Can-M, what's the dec of the zenith? Now imagine you're at either the North Pole, South Pole, or right on the equator as you're mulling through what the answer should be. So what declination would be exactly overhead from the North Pole or from the equator? So we're going to solve this together. We're going to turn on the zenith after turning off information. We're going to turn on the zenith from the sky and viewing options window. Recall, under markings, we're now going to click on zenith and nadir. And now zenith is at higher declinations. We're going to have to use the up arrow until capital Z, capital Z, plus sign, zenith comes into view. And what is the declination of our zenith? 10, 20, 30, 40, 49 degrees. I think you can figure out that the declination of the observer's zenith is always the observer's latitude. If you want some more challenges, what is the declination of the observer's horizon when facing due south and due north? I'll leave that, as I said, for you to figure out. Thank you for participating in these modules, and this concludes the module on the equatorial coordinate system.